This is the one-way ANOVA video on indicator variables. You can have a very satisfying life without ever knowingly encountering an indicator variable. We nevertheless introduced the topic for three reasons. First, as an element of statistical culture. Indicator variables provide the mechanism for unifying the treatment of continuous and categorical predictors. There's nothing wrong in knowing about this. Second, some of the papers you'll encounter in literature report the results, either explicitly or implicitly, in terms of indicator variables. Finally, for non-standard applications, you might have to create the indicator variables yourself. Even if the you is your statistician or your programmer, understanding the basics of this topic can make you a more effective collaborator. So what's the unifying idea here? It's that for all models with a continuous outcome, the basic mathematical model is the same, namely the usual regression model y equals a plus bx, as if the predictor or predictors are continuous. The only thing that changes for categorical predictors is that categories are replaced by the values of indicator variables. In fact, it turns out that even the intercept from a traditional regression model is based on an indicator. This slide presents the same ideas using a few more symbols. The key point is that the regression coefficient, sometimes called the beta coefficient, has a different interpretation depending on the scale of measurement of the variable with which it is associated. For a continuous predictor, the regression coefficient represents a slope. For a categorical predictor, the regression coefficient is either a group mean or the difference between group means. More generally, the regression coefficient is derived from the pattern of group means. This slide illustrates how to create the indicator variables for a one-way analysis of variance with a three-category predictor. The first indicator variable, x0, has a value of 1 for everyone. The second indicator variable, x1, is a 1 for everyone in group A and a 0 for everyone else. The third indicator variable, x2, is a 1 for everyone in group B and a 0 for everyone else. So long as an intercept is included, a one-way ANOVA with k groups requires exactly k-1 indicator variables. This slide plugs in the zeros and ones and thus illustrates that the indicator variables really work. As mentioned before, everyone in group A receives the same set of indicator variables, everyone in group B receives the same set, but different from those of group A, and so forth. We've plugged in the zeros and ones for everyone, and it turns out beta 0 represents the predicted mean for group C, beta 1 represents the difference between the predicted means of groups B and C. Beta 2 represents the difference between the predicted means of groups B and C. When beta 1 and beta 2 both equal 0, all of the group means are the same. Thus, the null hypothesis in the one-way ANOVA is that beta 1 and beta 2 are both 0. This is in a direct analogy with null hypothesis in a standard regression model with continuous predictors. Group C is sometimes called the reference group. It doesn't really matter which group is selected as the reference, nor does it matter whether the indicator variables use zeros and ones, zeros and minus ones, ones and minus ones, or something even more esoteric. If you're creating your own indicator variables and have a preference about which group to make the reference, the easiest thing to do is give it a code with the last alphanumeric level in your dataset. Understanding indicator variables will help you make sense of the output from statistical packages such as R and SAS. What you'd see on a typical output is the rightmost three columns. In other words, you'd have to work backwards to fill in the beta 0, beta 1, and beta 2. Exactly how the variables are labeled depends on the software package. Translating from the above example, you can work backwards to derive the group means. Group C is the reference group and thus has a mean of 100. Group A's mean is 100 plus 30. Group B's mean is 100 plus 20. Moreover, you can combine the regression coefficients and their standard errors into confidence intervals. For the confidence interval for the difference between mean outcomes in groups A and C, the inputs are the regression coefficient of 30 and the standard error of 10. For a large sample, take the 30 plus or minus 1.96 times the standard error, as illustrated on the slide. The 1.96 is derived from the normal distribution. For small samples, replace this 1.96 with an appropriate benchmark from the t-distribution. The resulting confidence interval will be somewhat wider than the one that's based on normal theory. As the above indicator variables are defined, they generate comparisons between groups A and C and B and C, but not between A and B. If the latter comparison is also desired, the simplest thing to do is to run another analysis with a different set of indicators. This is a legitimate thing to do. As long as you have the right number of indicator variables, you'll get the same results regardless of which ones you use. As a reminder, the right number of indicator variables is the number of levels minus 1.